Okay. I hope everyone had a good break. We're kind of like in the last stretch of the semester at this point. We just have 1 month left. I think classes end May 6th, so we're just like 1 month away pretty much. So today, and maybe a little bit tomorrow, we're going to be finishing the section on differential equations. So it's going to be finishing chapter 9. So the next exam is going to be Friday of next week. And so we'll have like the normal review for the exams like we've done for the previous exams. So I think Monday we'll continue going over new material, but then Tuesday we'll go over an exam review. Then Wednesday there'll be a practice exam. That's kind of like a group work. And then Friday will be the exam itself. So I think on, I guess Friday, we're not gonna have a group work this Friday because I need to cover material. I'm kind of like anxious about covering everything in time. So like this Friday, there won't be a group work, but there'll be one next week. And then in terms of like what's going to be on the exam, it's just going to be chapters 8 and 9. So there'll be sections 8.1 to 8.3. And then there'll be like the differential equation stuff that I talked about before break, and then what I'm talking about today and tomorrow. But there'll be an exam review like any other week. So it should be pretty clear about what's going to be on the exam and what you should be prioritizing. Okay, so with the, as there wasn't class yesterday, I decided to push the homework to 11:59 p.m. tonight. There's originally 15 problems. I got rid of a problem that has to do with like someone skydiving because we didn't do it in class. So there's only 14 problems on the homework, but some of these differential equation problems can be a little bit long. I was planning on going through 2 problems today. So the first problem I wanted to go over was this example at the end of the notes from Wednesday's class. So this is at the end of, I think, section 9.2. It's the final problem in that packet. So it's like in the notes, but it's also a homework problem. The numbers are just changed a little bit. So if you know how to do this problem, you'll know how to do the homework problem as well. So this problem, I think, is probably the hardest problem on the homework, and it requires thinking that wasn't really found on any of the problems that we did in this packet, or at least like it extends on the thinking we've done in a new way. So this is kind of like a forensics problem in a sense. So like we're detectives, it's 10:30 a.m. We discover a dead body in a room and we measure its temperature at 26 degrees Celsius. Then 1 hour later, the body's temperature drops to 24.8 degrees Celsius. And we want to determine the time of death. And so we're assuming the ambient temperature, so the room temperature, is going to be 37 degrees Celsius. Oh, never mind. This is, I was reading this incorrectly. So we're assuming the body's temperature was a normal 37 degrees Celsius. And then we're assuming that the temperature in the room was held constant at 20 degrees Celsius. So this is the ambient temperature. So we want to be using Newton's law of cooling for this problem. That's the first thing you should recognize, due to the fact that we have like this temperature that was initially at 37 degrees that decreases to 26 degrees and then 24.8 degrees. So we want to be using this law of cooling that we talked about earlier in this section. So this is, let's look at the actual page. So I think this is on page 9 of these notes. We're going to be using this equation right here. So we have y prime is equal to minus k, where minus k is this cooling constant, times y minus t naught, where t naught is the ambient temperature. So the first thing we can do is we can fill in some of the blanks. We know what t naught is going to be. I think it was at 20 degrees. And then we're going to have to determine what this k is going to end up being, which is the hard part of this problem. Okay, so from this law of cooling, we have that y prime is going to be equal to minus k times y minus t naught. And then we have that t naught, it was given to us in the beginning of the problem, is equal to 20 degrees Celsius. So this is equal to 20 degrees Celsius. So this is really equal to minus k times y minus 20. So this is a differential equation of the form of minus k times y minus b, where in this case our b is equal to 20, and then we don't really know what this k is, but we have this minus k here. So we know what the general solutions to these differential equations look like. they're going to be given by y sub t. I think I use, yeah, let's use t as our variable. So y sub t, this is going to be equal to 20 plus some constant c times e to the minus kt. So where I got this equation is just the first page of the section 9.2 notes. It's what we derived in the very beginning, right? If we have a differential equation of this form, like dy dt is equal to k times y minus b, the solution is always of the form of c times e to the kt power plus b. So in this case, our b was equal to 20, and then k was equal to minus k. So I had c times e to the minus kt power. So I'm just using the very first thing we derived in section 9.2. Okay, and then we have, oh, I'm getting lost. Okay, so now we need to determine what k is going to be. Before we determine what k is going to be, we should determine what c is going to be. I haven't passed out these notes yet. I'll do it later. I probably. Let's. Oh yeah, that's right. Okay, yeah. So this is equal. So we want to determine what c is going to be. We have some initial conditions. For instance, we know that the body's temperature was equal to 37 in the beginning. So this tells us that we have that 37 is equal to y evaluated at 0. This is equal to 20 plus c times e to the minus k times 0, which is just equal to 20 plus c. So we have, if you condense this equation, we have 37 is equal to 20 plus c. So you can solve for c by just subtracting both sides by 20. So this will tell us that 37 minus 20 is equal to c, i.e. c is equal to 17. So we're getting a little bit closer. We're getting more and more information about what our solution looks like. So we have y sub t is equal to 20 plus 17 times e to the minus kt. And then this is kind of the hard part. The hard part is determining what this k is going to end up being. Before I continue, are there any questions about how I found what y of t is up until this point? Okay, so we're going to try and solve for k. Before I continue, I'm going to let t naught, this is going to be equal to the time of death. So this is what we're trying to figure out. And we already know some information about the temperature at the time of death. Or I shouldn't say, oh, well, let's see. Let me reread this problem. Okay, well, I guess this isn't the time of death, actually. This is the temperature when they discover the body. So this is time when they discover the body. Okay, so there's some things we know about this, right? We know that at y, like y sub t naught is going to be equal to 26 degrees Celsius from the first sentence, right? They discover the dead body in a room and measure the temperature at 26 degrees Celsius. So what this means is they have 26 is equal to y evaluated at t naught. So this is going to be equal to 20, oh, that was weird, 20 plus 17 times e to the minus k times t naught. And so we can solve for t naught. Or, oh yeah, we will say we're not solving for t naught here. We're going to like write this out in terms of k times t naught. Like let's just see what we can do, right? We have two unknowns. Let's see what we can do with it. So what we're going to do is we're going to subtract both sides by 20. So this tells us that 6 is equal to 17 times e to the minus k times t naught. We can divide both sides by 17 to get that 6 over 17 is equal to e to the minus k t naught. We can take the natural log of both sides to get rid of the e on the right-hand side. So this will tell us that we have that the natural log of 6 over 17 is equal to minus k times t naught. And then we can multiply both sides by -1. So we ultimately have that minus the natural log of 6 over 17 is equal to k times t naught. So there isn't much we can really do with this information at the moment, but we have some additional information that we can play around with. So that way, eventually we can make use of this equation that we have here. So we know that y evaluated at t naught is equal to 26, but then we also know that after an hour has transpired, the body's temperature decreased to 24.8 degrees Celsius. So what this means, so we have this first piece of information, and then I'm going to do this other piece of information in red. So we have 24.8. This is equal to y evaluated at t naught plus 1. So we have like an additional hour. And we have that it's going to be equal to this temperature. And then we can follow the exact same process and write like k and t naught in terms of like this number 24.8. So this is telling us that this is going to be 20 plus 17 times e to the minus k times t naught plus 1 is equal to 24.8. And now we're going to write, like we're going to go through the same algebraic process, like we'll subtract by 20, we'll divide by 17, we'll apply the natural log, and then we'll multiply both sides by -1, just as we did up here above. And so what ends up happening is we'll end up seeing that this is going to give you minus the natural log of 4.8 over 17 is equal to k times t naught plus 1. So that was I'm just doing the exact same process we did before. I'm just condensing it into a smaller number of steps, right? So this is the exponent we have here. And I'm instead going to write this as being equal to k times t naught plus k. And so now we can see that there's going to be a way in which we can determine what k is going to be if we combine these two equations with one another, right? If we did k plus k times t naught, like this term here, and we subtracted it from this term here, we would end up getting k. And we have that this is a number, and this is a number as well. So combining these two equations with one another, we can determine what k is going to end up being. Right, so we have that k, so this will be in green. We have k, this is equal to k times t naught plus k subtracted by k times t naught. So we know what this number is equal to. It's this thing right here. So this is going to be equal to minus the natural log of 4.8 over 17. And then we're subtracting from this quantity this k times t naught. So k times t naught is equal to minus the natural log of 6 over 17. So this is really plus the natural log of 6 over 17. Right, so this is just going to end up being equal to a number, and that number ends up being equal to 0.223. Okay, so this tells you what your k is going to end up being. And so now we can finally say like what our equation is. So we finally found the general solution, right? So we have y sub t, we have all the pieces of information we can possibly want. So this is going to be equal to, what was it? So this is 20 plus 17 times e to the minus 0.223 times t. Right, so I'm just looking at this equation we had before, and then just plugging in k is equal to this 0.223. So we end up getting this equation for y sub t. And then it's just a matter of solving for t at this point. So we want to determine what the time of death is going to end up being. And so if we want to determine the time of death, we need to solve this equation for when t is equal to 0. Or I guess not t when t is equal to 0. Wait, what? I think I like labeled something incorrectly. So I think when I was solving this problem, I think I set it equal to 26, but 26 is equal. Let's see. Sorry, I think like the confusion I'm having right now. So I'm pretty sure I did it correctly, but I'm like just misunderstanding like the concepts here. So like we're saying we're examining the dead body in a room and we discover the temperature to be 26 degrees. And so what I ended up doing is I found K. It's like I feel like I just solved like the time when they discovered the dead body. But I guess like from there, I guess this is what I did, but I don't think this is correct. Right, because what I did was I did 26 is equal to y, evaluated at t naught is equal to 20, plus 17 times e to the minus 0.223 times t naught. But t naught was the time in which like the detectives discovered the body, and not the time when it actually like the person passed away. So I don't think this would actually give you like the right answer. But this is like the answer that they had in the book, so it makes me feel like it's like messed up a little bit. But I guess maybe I need to look into this again actually. So this is like 6, and you'll go through the exact same process. Like you'll end up solving for t naught in this case. So like this is 6 is equal to 17 times e to the minus 0.223 times t naught. And then you'll go through the same process we were doing before. So you get like minus natural log of 6 over 17 is equal to minus 2.23 times t naught. And then you'll divide both sides by minus 2.23. Oh, there shouldn't be this minus sign in front. You'll divide both sides by 2.23. This is minus natural log of 6 over 17 over 2.23 is equal to t naught. And then this ends up being equal to 4.667, which would imply that the death occurred 4 hours and 40 minutes ago. So this is about 4 hours and 40 minutes ago, which is around like 5:50 a.m. But again, I feel like this t naught that we solve for wouldn't actually be. I feel like it wouldn't be accurate in this case. Let me look through it again after class, and I'll send it. Yeah, right.
So you solve for when the body's temperature is normal at 37. Like, because I'm trying to find the time at which it died, which would be at 37 degrees, because that's what it says.
But then it would just be like you'll just do t is equal to 0 in that case. Because like if we're just like equal, if we're like thinking about it in the beginning, like the initial temperature, like the normal temperature is 37 degrees. So if you set it equal to 37, you'll just have that t would end up being equal to 0. Yeah, so this would give you the time in which they discover it. Let me look through it again after class. Like I'll do it right after class and I'll send out an email. Unless there's, oh yeah, Andrew.
That's like what it asks in R, how long it is since the body died, like when they found it. So you would be found T naught.
Well, I think there's like a difference between like finding it and when like the person actually passed away though. Because I think like the question is like maybe the person like the let's see. Like they're saying that they discovered it at 10:30, but like the results here, like I think this is the correct answer, but I don't understand why we would have like T naught is equal to 26 degrees, I suppose. It's like 26 degrees is the temperature at 10:30 a.m. So like I feel like this time should give you what the temperature would be at that time. Because like I think I'm just like confusing myself. Like I know this is the right answer, but I'm like I feel like there's something wrong with the problem, which I need to.
6 over 17, right? So that's coming from. you said you were 26, yeah.
Wait, the 6/17, like this part here? Or, wait, where's the 6/17 coming from?
Yeah.
Yeah, I feel like I'm making like a simple misunderstanding somewhere. I don't know. I'll look into it again. I'll send you an email. Maybe I might take this off the homework. I don't know. We'll see. I'm gonna look at this right after class during office hours, and I'll send out an email and it'll clarify. Yeah, sorry. I don't know. For some reason I'm like messing this up. But I think this should end up giving you the answer. I just don't know. It doesn't make sense to me, like why that would give you the right answer, I suppose. I guess like before like moving on, are there any questions about, I guess like the computational parts of the problem? Yeah, sorry, I should have thought about it a little bit more. I thought about it like last week, and then I haven't thought about it since. So it made sense to me at the time, and it doesn't make sense to me anymore. Okay, I'll go through one more homework problem. It's like someone asked me about this problem, so I'm going over this problem, and then we'll start doing your stuff. Okay, so this one's a little bit nicer. At least there's like no conceptual stuff going on. So for this problem, we have y to the 8th problem, or y to the 8th times dy dx is equal to x to the minus 6th power. And then we have this initial condition of y evaluated at 1 being equal to 0. And it wants us to solve this equation. And so this is a differential equation you can just solve by separation of variables. So what that means is anything with a y, you want on one side of the equation, and anything with an x, you want on the opposite side of the equation. So this one, you don't have to do too much work in this regard. You just have to multiply both sides by dx. So we have this original equation. I already have it written down, actually. So to go from here to here, all I did was just multiply both sides by dx to get this equation. And then once you have your variables separated from one another, you integrate both sides. So we have the integral of y to the 8th power dy is equal to the integral of x to the minus 6th dx. With both of these, you just need to use the power rule. So the integral of y to the 8th is just 1/9 times y to the 9th power. Then this is going to be equal to minus 1/5 times x to the minus 5, right? We take this minus 6 and we add 1 to it to get the minus 5, and then you divide by the minus 5, so you get this minus 1/5. And then we want to solve for y, which makes things a little bit weird because you have the 9th power here. So the first thing we can do is we can multiply both sides by 9. If you multiply both sides by 9, you have y to the 9th power is equal to minus 9/5 times x to the minus 5. Oh, I forgot my plus c. So there should be a plus c, like some constant. If you multiply both sides by 9, you just get 9 times c. So you can still just keep it as a constant. You can like absorb it into the constant is the term that they use. And then if we want to determine what y is, it's just a matter of taking the 9th root of both sides. So we have y is equal to the 9th root of minus 9/5 times x to the minus 5 plus c. And so at this point, we're almost done. Like this is the general solution that we're looking for, but it wants a specific solution because it gives us this initial condition of y evaluated at 1 is equal to 0. And so if we have y evaluated at 1 is equal to 0, this tells us that 0 is equal to y evaluated at 1. This is equal to the 9th root of minus 9/5 times 1 to the minus 5, which will just be equal to 1 plus c. So this is really telling us that 0 is equal to the 9th root of minus 9/5 plus c. And so if we want to determine c, we really just need to make sure that this 9th root is equal to 0. So you just look inside of the root and you'll see you have a minus 9/5 plus c it has to be equal to 0. So this will tell us that C has to be equal to 9/5. So this implies that C is equal to 9/5. So once you determine what C is going to be, it's just a matter of looking at your general equation we had before, and then just plugging in C is equal to 9/5. So we end up having that Y is equal to the 9th root of minus 9/5 times x to the minus 5 plus 9/5. Yeah, so the tricky part is just messing around with what's inside of the root to find the constancy, or at least it's new. We haven't done an example like this, so I thought it would be worth doing in class. Okay, any questions about this problem? Oh, okay. Okay, so those are some of the homework problems. Again, I'll look at the previous problem, the problem we just worked on, after class today, and I'll send out an email. I might take it off the homework, but I know some people have done it, and I don't want to have that work go to waste. So I'll think through it. Okay, so that's all I wanted to cover for section 9.2. So there's only 2 more sections I want to cover from chapter 9. Those are sections 9.3 and 9.5. 9.3 isn't super important. There might be an exam problem on it. So at most 5 points dedicated to section 9.3 on the exam. But it's quick, so I thought I'd just go over it anyways. And then section 9.5 is the last kind of differential equation we're going to be solving in this class. It's a little, like, it looks bad. A lot of the problems might take a decent amount of time, but you just follow the same steps every single time for every single problem, and they all play the same. So it's more of like that you get enough practicing more than you understand. Like conceptually. Okay. So I'll break it maybe like halfway through what I want to go through for differential equations today. So there's only just like one example I want to do from section 9.3, and then 3 from section 9.5 extra. Thanks. Okay, so on section 9.3, we're going to be talking about slope fields. So slope fields are kind of like a visual way of understanding the solutions to a differential equation. They're going to be helpful in that, or at least if you're taking differential equations in the future, you're not always going to have explicit solutions to differential equations. Sometimes you might have no solutions, and the best you can do is approximate solutions. Or sometimes you're going to be faced with a differential equation. You don't have the techniques to solve, but you can still graph what the solutions are going to look like via these slope fields. So they give you an intuition of what solutions to differential equations are going to look like, even if you can't solve the differential equation. So everything you need to know about slope fields is really just on this first page. And then the next page, we compute an example. But usually when you're computing slope fields, you just want to put it into like a graphing calculator that you can find online. Okay, so the context for this section is we're going to let t be an independent variable. So that just means it's a variable that doesn't have any relations with the other variable y. So like this unknown equation y. And so a first order differential equation can then be written in the following form. So a first order differential equation is just any equation where you have the derivative of some function as being equal to some other function. So we have a first order differential equation dy dt, which we're writing as f of ty. So it's a function in terms of 2 variables, t and y. And so what this is telling us, like if we have this equation, it's telling us that this f of ty function is going to give you the slope of the graph of a solution, y is equal to y sub t, at some point ty. So this f of ty is just a function that records all of the slopes of all solutions you have for your differential equation. So it sounds really complicated, but intuitively what's going on is that like this function f of yt is it's kind of like a set of instructions that guides the solution to the system of differential equations. And so there's a visual at the bottom of the page. And you can kind of, everything you need to know about slope fields, you can just see from this picture here. Maybe it's a little bit difficult to see, but like each of these little lines here give you a slope, and this part of the rectangle or this part of the square. And then these red lines are solutions to some sort of differential equation that isn't explicitly spelled out. So you can see that these solutions in red are guided by these little lines that we have, these little blue lines. In fact, the solutions to the differential equation in red have to be tangent, or like these blue lines have to be tangent to these solutions, which is hopefully something you can see. And we'll compute an example that will make it more clear later on. And so you calculate or find these little blue lines by looking at f of ty. So each segment, i.e. each of these blue lines, has slope f of ty. And then the solutions to this differential equation, dy dt is equal to f of ty, must have graphs that are everywhere tangent to the slope field, i.e. everywhere tangent to these little blue lines that we have. Okay. So I think it helps, like we're just going to go through a single example to illustrate like how you compute slope fields. But again, like I said in the beginning, I don't really, at most there'll be 5 points on the exam dedicated to slope fields. I'm still undecided about whether or not I'm putting on a slope field problem. So you should know it, but it isn't a very high priority thing that you have to know. Okay, so for this example, it wants you to draw the slope field for dy dt is equal to minus ty. So the first thing you do is we already have a differential equation in the form of dy dt is equal to some function in terms of minus t and y. So we're just going to let f of ty, this is going to be equal to minus t y, right? Is this the function that was given to us? And then once we have f of ty defined in this way, we're just going to compute some sample values to give an idea of how the solutions are going to behave. So I have a bunch of sample values listed out already. So I'll just compute some of them. So it's really just like t is equal to -1. What are some sample y values? What happens when t is equal to 0? What are some sample y values? And then all the way up until t is equal to 2. So I'm choosing as the sample values. And so if you want to determine these sample values, all you do is if we want to determine what f of -1 is, we plug in -1 in for t, and then 1 in for y. And so this is just going to end up being equal to 1. Let me put a little bit more space here. So this is equal to -1 times -1 times 1. So this is equal to just 1. And so in terms of the slope field, what this tells us is if we look at the point -1, 1, so I made this little rectangle here that records these t values or y values and the t values horizontally. We just find the point -1, 1. So that's this point right here. And then we just draw a segment that has slope 1. So something like this. So this is slope 1. And then you do the same thing for all of these other values. So I'm going to go a little bit faster, but you can see for the next point, we have -1, 0. So y is equal to 0. So you would have -1 or -1 times 0 is just going to be 0. So the slope is going to be 0. Let me choose a color that stands out a little bit more. So we have this yellow. I guess I'll do everything in yellow. Why not? So this 0 corresponds to this slope 0 segment. And then if you plug in t is equal to -1 and y is equal to -1, you would end up just getting something equal to -1. So this will be -1. So this will be slope -1 like this. And then you just continue this process. The next one's even easier because we have t is equal to 0 for all of them. So it's going to be 0, 0, 0. So at the point 0, 1, which is around this point I'm highlighting here, is going to have a slope 0 like this. At 0, 0, we have a slope 0. And at 0, -1, we have a slope 0 as well. So that's these segments. I'll give you these various slopes or segments of the slope field. And then we just continue onward. So f of 1, 1 will end up being equal to -1. F of 1, 0 will end up being equal to 0. F of 1, -1 will end up being equal to 1. So we get slope fields that look like this. So slope -1. We get slope 0 at 1, 0. And then we have slope 1 at 1, -1. So it looks like this. And then the final set, we have f of 2, 1 is going to be equal to -2. F of 2, 0 will be equal to 0. And f of 2, -1 will be equal to 2. So at 2, 1, we have a slope of -2. So this is going to be a little bit steeper than the previous arrow. Then we have f of 2, 0 is equal to 0. So we have a horizontal line. And then f of 2, -1 is equal to 2. So have a slope of 2. Okay, so this gives you an idea of what the slope field is going to end up looking like. Right, so if you wanted to trace an idea of what the solution to this differential equation is going to look like, you see that the arrows are pointed to the right and kind of like diagonally a little bit. So it looks something like this. And then we have a 0 slope. And then it goes downwards. And it continues going to the right like this. So this is kind of what a solution, I mean, it's just ballparking, but this is kind of what a solution would end up looking like for this differential equation. So this is an approximation of a solution. And so if you put this into some sort of calculator you can find online, like if you just Google slope field graph, you can find one on Desmos, and then you can plug it in, like this equation minus ty into that equation, and you would end up getting the following slope field. So this is the complete slope field for the example we just computed. You can see there's obviously a lot more detail, but the general idea kind of holds, right? So on the y-axis, all of the slopes of the lines are horizontal, so they're just completely flat. And you can see like the solution kind of goes like this if it follows the arrows. And then on the right, there's some graphs of specific solutions, right? So each of these red lines on the graph give you a specific solution to the differential equation. And you can see that these solutions to the differential equation, they follow these blue lines that we outlined. Okay, yeah, so the reason I'm not spending that much time on this, it's like if you take differential equations, you'll spend a lot more time on it. And then also, like really you just compute slope fields by putting it into a computer pretty much. Like you want to find the slope field, you never really sit down and just write out these arrows. You just put it into a computer where you get like a lot more information. But I guess like the important thing is you understand what the slope field is telling you. Like if you get a picture of a slope field, you know what the solutions are going to look like. So if I were to ask a problem on the exam about slope fields, I'll probably give you a picture like this, and you would have to trace a solution or like what a solution would look like from that picture. But I don't plan on doing anything too crazy with them. Okay, any questions about this example? Okay, and maybe I should do, maybe it's kind of, I feel like you probably understand in order to get what's going on, but I feel like I should do at least like one demonstration of like how you can do it online, because it's pretty straightforward. So if you just look up, you can use like, I like using Desmos, like you just look up Desmos slope field. There'll be a slope field generator. It's like the first response. And then they'll give you some function g of xy, which is equal to dy dx. Instead of x, we are using t, but it's the exact same idea. All you have to do is just change the function that they give you. So they have g of xy is equal to 2x over y. For our example, we were looking at minus x times y. You just put it in and boom, like you get the slope field, right? So you can see it's similar to what we were just computing by hand, but it gives you more information. And then you can track this thing around and you can kind of see like the slopes of each of these segments. So this was slope 1, 0, -1, -2, just like we were computing by hand a moment ago. Okay, any questions before moving on? Okay, if you do differential equations, which is kind of like Calc 4, you'll have to know a lot more about these. But for now, this is it suffices for what we care about. Okay, so in the last 10 minutes, I want to maybe go through. I'll try and go through one more example. So this is the last section you need to know about for differential equations. This is looking at first order linear equations. This is going to seem pretty rough at first, but if you just get enough practice in, these problems are actually pretty straightforward, I would say. It's just going to be applying the same steps over and over again. So the more practice you get with them, the easier it will be. But if you don't do any practice with these, you're it's like really hard to derive this on the fly, like you could for the other differential equations. So I guess the setup for this one, in section 9.2, we investigated the first order linear constant coefficient differential equation. So differential equations of the form of dy dt is equal to k times y plus c. And so in this section, we're really looking at the same kind of differential equations, except now instead of us having constants, k and c are now going to be functions in terms of x, which is going to make things a bit more complicated. So some of these equations we're looking at can be or are separable and can be solved using separation of variables. But there's going to be plenty of examples where we have differential equations that are first order linear differential equations that can't be solved using separation of variables. So you have to use this technique. So just for notation, we have a first order linear differential equation is one that can be put in the following form. So this is important to remember. If you're doing the exam, like there'll be one problem like this on the exam, right? To use what we're going to be talking about today and tomorrow. So if you see an equation of the form of y prime plus some function of x times y on the left-hand side of the equation, and then on the right-hand side of the equation, you have some function q of x. This means that you're going to want to use the methods we'll be talking about today and tomorrow. And so this is why it's kind of hard to derive the solutions to the differential equations for this section versus what we saw in 9.1 and 9.2. So if we want to solve this equation, what we want to do is we want to multiply both sides of the equation by what's called the integrating factor. So the integrating factor is this function alpha x, which is going to be equal to e to the integral of px dx. And the dx should actually be within the integral or within the exponent, right? And so the reason why, like it seems like it's coming out of nowhere, and it kind of is. But if you multiply the left-hand side of this equation by this integrating factor, it ends up giving you a derivative that's easy to work with. So what ends up happening, and I'll show this within the next couple of minutes, is if we multiply both sides of the equation by this integrating factor, alpha x, we end up getting that alpha x times y prime plus px times y. This always ends up being equal to the derivative of alpha x times y. I feel like I should show this. I'll show it here below, and then you should copy it down, and then I'll erase it because it's going to be like I'll be going over this problem tomorrow. So like to prove this, if we do alpha x times y, if we consider this derivative, this is the same thing as doing the derivative of e to the integral of px dx times y. And so to compute this derivative, you need to use the product rule. So the product rule tells us that this is going to be equal to the derivative of e to the integral of px dx multiplied by y. And then this is going to be plus e to the integral of px dx times y prime. And so the derivative of e to the integral of px dx, this is going to be equal to px times e to the integral of px dx right? The derivative of any exponential function is just going to be the original function multiplied by the derivative of the exponent. So the derivative of the exponent is going to cancel out with this integral here. So you're just going to be left with px by the chain rule. So this is going to be times y. And then this is plus e to the integral of px dx times y prime. And so now we can factor out this integrating factor from both terms of the sum. So this is equal to e to the integral of px dx. And then this is times px y plus y prime. And so maybe I'm going to write it in a way that's more clear. So this is equal to, this is alpha x, right? Like this e to the integral of px dx was equal to alpha x. So I'm just going to write this as alpha x. So this is equal to alpha x times y prime plus px times y. And so you can note that this equation we have that's being multiplied by the integrating factor is exactly the left-hand side of this differential equation that we're considering. So like every time, so this is why it's hard to derive this on your own, because like who would have thought like you multiply both sides of the equation by this weird like alpha x formula, and when you multiply this alpha x by the left-hand side of the formula, you always end up getting the derivative of alpha x times y. So then if you wanted to solve a differential equation, you would integrate both sides, and now the integral just cancels out with this derivative here. I'm not going to have enough time to go through an example, but it's something we'll see on Wednesday. Like having it in this form ends up being very convenient, because now if you integrate, you just get alpha x times y. And so these are the 5 steps. I'll review this tomorrow as well, because I don't have enough time to go through an example. But you can always like if you have a first order linear differential equation, you always just follow these 5 steps. If you follow these 5 steps, you will always end up getting the right answer. It's like the first thing you do is you find the integrating factor. The second step is you multiply the equation by the integrating factor. The third step is you integrate. Fourth step is you solve for y. And then step 5 is you solve for the constant c using the initial value that they give you. So we'll continue this tomorrow. We'll go through the examples, and you'll see it isn't as bad as it might look. Okay.